Welcome back to our Science Corner Deep Dive series. We aim these discussions, at intellectually curious minds, amateur scientists like yourselves.
Glad to be here.
Today we're tackling something truly fascinating, I think. It's the science swirling around potential life on the exoplanet K218b.
Ah, yes, K218b. It's certainly captured a lot of attention recently.
For those catching up, it's about 124 light years off, over in the constellation Leo, orbits a red dwarf star.
And critically, it's in the habitable zone.
Right, that sweet spot where liquid water could theoretically exist on the surface.
Precisely, which is why it's such a prime target for study.
And the big news, the reason we're really digging in today, involves the James Webb Space Telescope, the JWST.
Indeed. The latest observations are suggesting something, well, quite provocative.
Which is the possible presence of dimethyl sulfide, DMS, in its atmosphere.
That's the molecule, yes, dimethyl sulfide.
And DMS. Well, here on Earth, that molecule really smells of life, doesn't it? Phytoplankton, the sea.
It does. On our planet, DMS is overwhelmingly produced by biology. Think tiny organisms in the oceans. They're a huge part of the ecosystem.
So finding hints of it out there, that immediately makes you think, well, could there be similar life processes happening light years away?
That's the tantalizing possibility, yes. It's why detecting it, even tentatively, is such a big deal.
Now, before this DMS finding, K218b was already flagged as a candidate for being what was the term? A Hyacin world.
That's right, Hyacin. It's a sort of portmanteau hydrogen atmosphere over a water ocean.
And that idea came from earlier JWST data, finding methane and carbon dioxide, right?
Exactly, CH4 and CO2. Those detections supported the model of a planet potentially covered in a global ocean with a thick, hydrogen-rich atmosphere, very different from Earth.
So how does this potential DMS fit into that Hyacin picture? Does it strengthen it or maybe complicate things?
Well, it certainly fits nicely with the idea of a water ocean, given the earthly analog of marine life producing DMS.
Makes sense.
But we have to be cautious. Science is always exploring alternatives. Could it be something else? Maybe a planet with, say, a huge magma ocean. Or perhaps it's not really a solid surface with an ocean, but more of a gas giant, just with some unusual chemistry.
So the Hyacin model is a strong contender, but not the only possibility on the table.
Correct. These new findings add a fascinating piece, but they don't close the case on the planet's fundamental nature just yet. We're still interpreting.
It really does feel like we're entering a new phase, though. With JWST, we're not just finding planets, we're starting to genuinely sniff their atmospheres for clues.
Absolutely. The lead researcher on this, Niku Madhusudan, he called it a revolutionary moment.
And you can see why. The idea of finding potential signs of life, actual chemical evidence, in other star systems. It's moving from science fiction towards observational science.
It truly is. And what's significant about this DMS finding is that it builds on earlier hints.
Ah, okay. So this wasn't completely out of the blue.
No. The team had previously seen some tentative evidence using JWST's near-infrared instruments. That would be NIRS and ENR-SPEC.
Near-infrared. Okay, so different wavelengths of light.
Exactly. They cover one part of the infrared spectrum, but this latest work adds data from MURI.
The mid-infrared instrument.
Right. MURI looks at a different, longer wavelength range of infrared light. Seeing a signal consistent with DMS in both near-infrared and mid-infrared data using different instruments, that strengthens the case considerably.
Because different molecules absorb light differently across the spectrum.
Precisely. And having MRI involved is particularly useful for certain molecules, potentially including DMS under these conditions. It gives us more confidence.
And this new data pushes the confidence level up to, what was it, 3 sigma?
Yes, 3 sigma. And they also mentioned tentative hints of another related molecule, dimethyl disulfide, or DMDS.
Okay, 3 sigma. For listeners maybe not familiar, what does that mean in practical terms? Is that discovery level?
Not quite discovery in the strictest sense, like particle physics uses. A 3 sigma result means there's roughly a 0.3% chance, about 1 in 370, that you'd see a signal this strong just due to random noise or fluctuations in the data, assuming your model is correct.
So pretty unlikely to be just random chance, but not impossible.
Exactly. It's significant evidence, makes you pay attention. But the gold standard in many fields, especially when claiming something extraordinary, is 5 sigma.
And 5 sigma means?
That translates to a chance of about 1 in 3.5 million of it being a random fluke. Much, much stronger. It provides a much higher degree of certainty.
Right. Like being almost sure it's real versus pretty sure.
That's a good way to put it. The team estimates they need maybe 16 to 24 more hours of JWST time observing K218b transits to potentially reach that 5 sigma level for DMS.
Which is a lot of precious telescope time.
It is indeed. JWST time is highly computed for.
It's still amazing we can do this at all. Detecting chemicals 124 light years away, how does JWST actually do that? What's the technique?
It's called transmission spectroscopy. It relies on the planet passing directly between us and its host star. That's called a transit.
Okay, like a mini eclipse.
Sort of, yes. As the planet transits, a tiny fraction of the starlight filters through the upper layers of the planet's atmosphere on its way to us.
Ah, so the atmosphere leaves a fingerprint on the starlight.
Exactly. Molecules in that atmosphere, water, methane, carbon dioxide, maybe DMS, absorb very specific wavelengths or colors of infrared light.
So JWST collects the starlight during the transit.
Spreads it out into a spectrum like a rainbow, and looks for these characteristic dips missing light at specific wavelengths. Each dip pattern is like a unique barcode for a particular molecule.
And having instruments like NIRAS, NIRASPEC, and MIR lets you look for different barcodes across a wider range.
Correct. It gives a more complete picture of the atmospheric composition.
So back to DMS. We're excited because on Earth, life makes it. It's a potential biosignature. But you mentioned earlier, it's not always a sign of life, is it?
That's the critical caveat, yes. While biology, especially marine microbes, is the dominant source here, we can't rule out non-biological abiotic ways it might form.
Like geological processes or weird chemistry we haven't thought of.
Potentially. There have been lab experiments suggesting abiotic pathways under certain conditions, and perhaps more tellingly, DMS has actually been detected on comets.
Comets. Okay, definitely not alive.
Definitely not. So that tells us DMS can exist in environments without life.
Which means finding it on K218b isn't quite a smoking gun for aliens just yet.
Precisely. It's a very interesting clue, a puzzle piece, but not proof positive. We need to be extremely rigorous.
Does the amount matter? Like, maybe life produces way more DMS than abiotic processes could.
That's one line of argument. Some scientists suggest that the level of DMS potentially detected might be harder to explain abiotically compared to, say, the trace amounts seen on comets. But
we need more data, more research into those abiotic pathways.
absolutely. We need to understand how much DMS could be produced non-biologically under the conditions thought to exist on K218b before we can weigh the likelihood of a biological source. And there's always the possibility of some other chemical mimicking the DMS signal.
Right, the complexity of analyzing light from so far away. Which brings us to that distance, 124 light years. It's just mind-boggling.
It truly is. For context, our fastest probes like Voyager or New Horizons would take literally millions of years to cover that distance.
So sending a probe to actually visit K218b, it's firmly in the realm of science fiction for now.
Completely. Direct exploration with current or foreseeable technology is, well, not feasible.
Makes you appreciate the power of telescopes like JWST even more. It's our only way to touch these worlds right now.
It is. Our tools are light and spectroscopy.
Though people do dream about future tech, right? Like
Yeah.
super fast propulsion, maybe using antimatter or something.
There are theoretical concepts, yes. Relativistic propulsion. Or even more exotic ideas like using the sun's gravity as a giant lens to get incredibly detailed images of exoplanets.
Gravitational lensing. Wow. But those are very, very long-term prospects.
Extremely long-term. For the moment, our focus has to be on refining our remote sensing techniques with telescopes.
Okay, so let's recap the key takeaways for our listeners. JWST has given us stronger hints now at 3 sigma confidence for DMS and K218b's atmosphere, possibly DMDS too.
Building on earlier detections using multiple instruments across different infrared wavelengths via transmission spectroscopy.
The excitement comes because DMS is a big biosignature here on Earth.
And it's a big but. We know it can exist without life, like on comets, and we need to rule out abiotic production on K218d itself.
More data is needed, aiming for that 5 sigma confirmation, while keeping in mind potential mimicking chemicals or model issues.
And remembering the immense distance makes direct study impossible for the foreseeable future.
So it leaves us with a really profound question, doesn't it?
It does.
Considering this molecule, DMS, could be from life or just chemistry, and we're trying to figure this out from 124 light years away, what's it going to take? What breakthroughs, scientifically or maybe technologically, do people think will be crucial to actually know definitively if there's life on worlds like K218b?
That really is the central question driving so much of astrobiology and exoplanet science today. What will be that key piece of evidence or that new method that finally answers it? Something for all of us to think about.